constant histone disassembly and assembly going on in cells, even outside of S phase, in part due to cope with this problem of DNA repair. And that's illustrated here. So if you have a lesion, in order to repair it, you need to make room, so you remove histones. And after it's been repaired, then you need to fill this gap with histones again. And again, histone chaperones are the guys who do this job. And again, there's a big overlap between the histone chaperones involved in this phase, chromatin assembly, and linear repair coupled DNA assembly. Okay. There's yet another reason why you need to do chromatin assembly outside of S phase, and that's the fact that you get gene transcription. And now we're moving more into my main expertise. So during transcription, the RNA polymerase has to deal with nucleosomes, right? There are nucleosomes everywhere. So the polymerase has to go through them in order to make a pre-mRNA. Okay. In order to do that, again, some histone chaperones come into play. Okay, and they will help the polymerase to deal with these nucleosomes. So there are histone chaperones, well-known histone chaperones such as FAC and SP6, for example, that will somehow disassemble. I'm saying somehow because we don't fully understand exactly to what extent it's really disassembled, but I would say at least reorganize the nucleosome in a way so that the polymerase can actually go through them. And most importantly, these same histone chaperones will make sure that these histones will be reassembled behind the polymerase. Otherwise, each time you would transcribe a gene, you would disrupt chromatin structure, and that means problem, right? So transcription is always accompanied by these histone chaperones, as well as some other enzymes that would modify these histones to coordinate their disassembly and reassembly during transcription. Okay, so that happens during transcriptional elongation. Constantly, chromatin is disassembled, reassembled in order to allow transcription. And that was known for a while, but what we discovered more recently, and my lab has been part of it, so I'm going to show you a little bit of experiments related to this, is the fact that at promoters, not the regions that are transcribed, but the regions that where the polymerase would actually assemble to initiate transcription, at these regions, for some reason that we don't fully understand, chromatin is very, very dynamic, much more dynamic than in transcribed regions. By dynamic, I mean that these nucleosomes are constantly falling apart and reassembling. So the expression we use to describe that is turnover. So the nucleosomes and promoters have a very high turnover rate. Okay, they form and fall apart at a very high rate, much higher rate than nucleosomes are outside of promoters. Okay. So I'll show you a key experiment that we actually performed to demonstrate that. So the question, the original question was, is there any histone assembly or chromatin assembly that we can detect outside of S phase? Okay. So because again, during S phase, you have, as I just said, you have linear propagation, so you have massive gene expression and chromatin assembly. But what about outside S phase? Okay. Notably during G1, because in G1, this is where you have most of your transcription. There's a lot of transcription going on. And again, the polymerase has to deal with nucleosomes, so there must be some mechanism to assemble chromatin during G1. So this work was actually in collaboration with Amine Nourani in Quebec. Some of you may know his lab. So where they actually created that system, which is very, very nice. So in these cells, these are yeast cells, okay? You have two copies of the histone. In this case, it's shown H3, but you can do the assay with any of the histones, okay? So the endogenous histone gene is driven by its own promoter, so its expression would be limited to the S phase, like any other histone. Okay. And we tag this gene with MYC. So we have an epitope so we can actually detect it. In these cells, we also introduce another allele of H3, but this one is under the GAL promoter, which means that we can control when it is expressed. Okay, so it would be expressed only when we feed the cells with galactose, and it would be off when the cells are grown in presence of glucose. Okay, and this histone, and that's important, is flagged with a different, is tagged with a different tag. In this case, it's a flag tag. Okay, so we can differentiate between these guys because there are different tags, and we have antibodies to recognize specifically MYC or flag. Okay. So if you grow these cells in normal media with glucose, this guy will not be expressed, and this one will be highly expressed in S phase. So your cells will essentially contain chromatin that's made of MYC histones, so blue chromatin. Okay. So the question is, can we observe regions where this guy will get in? If it gets in, it means that there's been some chromatin assembly going on. So the trick was to stop cells before S, so we're sure that the experiment is performed with cells that are not in S phase. Otherwise, we'll be confounded by the fact that in S phase there's a lot of replication, chromatin assembly going on. So we block the cells in G1. Then we switch them to galactose so they express the flag histone. And then we ask the question, is the flag histone incorporated in the genome? And if so, where? Okay. So for that we did chip experiments. I'm going to explain the chip in a few slides later on. At this point, I don't think you need to fully understand it to get the idea. Hopefully, that'll be fine. Okay, so we did a chip for MYC to monitor these histones and a chip with flag, and we hide them on a full genome binding array. And this is just a picture on the top of a snapshot of a small region of the genome that illustrates well what's going on. So what's showing here is the ratio of flag over MYC. So flag is the novel histones, and the MYC is the histones that were already there in the chromatin. So you see that this is not flat. So first of all, it tells you that some regions incorporate more of the novel histones than others. And as I illustrated by the dashed line here, you see that whenever you have a high rate of incorporation, this is always falling between genes. So essentially, it's in promoter regions. Okay, and this is just an aggregate showing you if you aggregate all the genes together. To look at the average signal, this is what it looks like. So you have a lot in the promoter and very little in the gene body. And here the genes are stratified by their expression rate, essentially. So you see that at the promoter, the more a gene is expressed, the more histones are turning over. Okay, and you see that in gene body, turnover is very low, except for genes that are very highly expressed, and that's because of the pathway I described earlier. That when polymerase transcribes through, it disassembles nucleosome and reassemble it in the wave. Okay, and this, except for the very highly expressed gene, this happens without incorporating de novo histones. Okay, and that's because you have these chaperones that their job is to actually recycle the histones and reassemble them at the back. So these chaperones, in fact, is 56. So they recycle the histones so that the new guys that are flagged don't have a chance to get in. Okay. At promoters, however, you don't have the system to make sure that you keep the same histones. We think that, on the contrary, there are mechanisms to favor histone exchange at promoters. Okay, and that's probably important for epigenetic regions. And I may get back to this later, but since we haven't introduced the notion of epigenetic at this point, I don't think I should discuss it at this point in the lecture. But anyway, just to say that different regions of the genome use different pathways for chromatin assembly. In gene bodies, you have chaperones that make sure that you recycle the histones. And at promoters, there are probably pathways that, on the contrary, favor eviction of current histones with and replenishing the chromatin with new histones. Okay. Another important concept in chromatin biology is in the concept of nucleosome partitioning. So these nucleosomes, you saw they look like. I told you that they are assembled by some chaperones. But where do they live in the genome? So are they just randomly incorporated in the genome, or do they live in precise locations? Okay. Until very recently, there was no answer to this, but thanks to new technology that I'm going to explain in a minute, we can now map these nucleosomes in the genome very precisely and figure out where they are. But prior to this, we already knew that DNA sequence had something to do with this, because people have assembled nucleosomes in vitro using different sequences. And they realized that some sequences, they assemble into nucleosomes very easily. But some sequences are just very refractory to wrapping around histone aptamer. And by comparing these sequences, people realized that the ideal sequence to wrap into a nucleosome is actually sort of an alternation between these AT-rich dinucleotide and GC-rich nucleotide. And this is because these AT-rich sequences are very stiff. They don't bend. The AT-rich are very bendable, whereas the GC-rich sequences are very stiff. So by having this alternation of rigid and flexible, you get the perfect sort of behavior of the DNA, so that it can actually be wrapped around the aptamer. So that suggests that some DNA sequence can favor assembly into a nucleosome, and others would disfavor assembly into a nucleosome. But does that dictate where nucleosomes go in the cell? Can we, just by looking at the DNA sequence, predict where nucleosomes should go? Right? So people have tried that, and there are papers that claim that yes, and other papers claim that no. There's big debates around this, and it's only recently that I think experiments have started to address how that works, and I'll show you just one of these key experiments in a minute. But the question remained open for a long time. First of all, where do they go, these nucleosomes, and is it dictated just by DNA sequence, or do cells use proteins to actually help to localize these nucleosomes? Okay, so to get to these answers, you need to be able to map where the nucleosomes live in the cell. So that's there are a few methods, but this is the most widely used method for that, and that's called MNase-seq. Some of you were in other class that I taught, so you already know about this. But for the others, I'll just briefly explain how that works. So this makes use of this enzyme MNase, macroprotocol nuclease, and the property that this enzyme has to preferentially digest free DNA as opposed to nucleosomal DNA. Okay, so essentially the DNA that's wrapped into nucleosome is not as accessible for the enzyme. So if you digest chromatin with limiting amount of the enzyme, it would preferentially cut between nucleosomes as opposed to within nucleosome, right? So it's sort of footprinting kind of idea. So you can exploit this to map where the nucleosomes live in the cell. So essentially you isolate chromatin from the cell, you submit it to limiting digestion with MNase, and that's what it looks like. In this case, it's a time core, so and this is just an agarose gel looking at DNA. So you see this ladder, okay? So this is the nucleosomal ladder. So this band has 146 base pair. It's actually corresponds to the DNA around one nucleosome. And then this is twice the size. It's actually two nucleosomes tied together with a linker, and that's a tri-nucleosome, and so on. Okay. If you were to digest full spin, you will only get this guy. You would even get shorter because at some point the enzyme managed to actually chew even the DNA that's wrapped around the nucleosome. But if you do limited digestion like this, get monodyne trinucleosomes. You can cut this band, which corresponds to mononucleosome, and sequence the DNA using high-throughput sequencing. So you get millions and millions of short sequencing reads that you can align back to the genome and see what it looks like. And when you do that, this is a map of read density along the region of the genome. Okay, so essentially you see these peaks. So you sequence very often this region you don't sequence as often and so on. Okay, so this is read density, and this is just coordinate along the gene. So essentially what you see are these peaks and troughs. And because the MNA's digestion is protected by nucleosomes, the interpretation of this data is that every time you have a peak, this is where you have the nucleosome sitting. And whenever you have a valley, it means this is very easy to digest DNA, so it's regions between nucleosomes. So by lining up these peaks, you can determine where the nucleosomes are localized in the gene. Okay. And coming back to the notion of nucleosome positioning, by positioning, what we mean is where does the nucleosome live along the DNA, okay, in this axis. And any given nucleosome can be well positioned, meaning that in your cell population, it's always positioned at the same place, in which case it will give you a very nice, sharp peak in this assay. But not the same, but another nucleosome could be much less well positioned, meaning that in a population, it may sometimes sit here, and sometimes sit there, and sometimes sit here. So if you look at the population as a whole, the signal here will give you much lousier peak. And you have regions like this where you can still see preferable sites for position to sit, but it's not nearly as well defined as these regions. So these are referred to as fuzzy nucleosomes. Their position is fuzzy. And the notion of nucleosome positioning is totally orthogonal to the concept of nucleosome occupancy. And when you read papers, you have to understand the difference between the two. Nucleosome occupancy refers to, in your population, what's the fraction of the cells that has a nucleosome in a given region. Positioning refers to where exactly its position is that nucleosome position. So you can have regions very high occupancy and very low positioning. This, for example, there's a lot of histones around here, but the localization is positive. This region also has high occupancy, but it also has high positioning. And you could have regions where you have very high occupancy and low positioning. And, these are two separate concepts, and they are very, very often mixed up by people. That's why I insist on this. It's a very different concept: positioning and occupancy. Okay. All right. Okay. Too long here. Okay. So coming back to the $1 million question, in the cell, what tells the nucleosomes where to go? Is it just the sequence, the fact that you have more bendable and less bendable regions, or is there any proteins, factors in cells that actually will use energy to move nucleosomes around and decide where to go? So these guys published a paper a few years back where they addressed this question in a very nice experiment. Essentially, they did these MNA-seq experiment that I've talked to you about and compared the pattern you observe when you look at the chromatin that you extract from a cell and chromatin that you assembled in vitro without any other factor than the histones. Okay, I told you earlier that if you do it properly, you can assemble nucleosomes in vitro. You first make octamers, you express the 4 histones, you make octamers, you give it DNA and in proper salt, and then you dialyze slowly, and nucleosomes will form. And they will go to their favorite position given the DNA sequence that's around. Obviously, if you have a very stiff DNA, you'll find nothing there. In other regions, you'll find nucleosomes. So they're positioned somewhere, and there's only DNA in there. So it will position wherever the DNA is more favorable for positioning. The question is this position the one you observe in vivo or not? So that's the experiment. So in vivo chromatin, in vitro chromatin, digest with MNAs and deep sequence, and so on. In this representation, you don't see it because there are too many, but there are actually rows. Okay, and each row represents a gene. And this axis gives you distance from, in this case, it was aligned, I believe, on the transcription start site for every one of these genes. So somewhere here is the initiation of transcription, and these here are is a heat map representation of read density. Okay, on the previous slide I showed you read density as peaks like this. Here is just illustrated as a heat map, as a color code, so that you can look at 6,000 genes at the same time versus just one. Okay, so essentially, whenever it's yellow, it means that you are on a peak, and whenever it's blue, it means you're in a valley, and black is in the middle. So essentially, in cells, that's the pattern you get. You get a very typical pattern of nucleosome positioning around the gene. Right at the promoter is no nucleosomes. It's blue. This was known before. It's referred to as the nucleosome-free region in promoters. And right next to this nucleosome-free region, there's a very well-positioned nucleosome. You see that in all these nucleosomes, in all these promoters, there's a nucleosome that sits right after this nucleosome-free region. And then you have another nucleosome and another one and so on. And the further away you move from the promoter, the fuzzier are the nucleosomes. There are not fewer nucleosomes here than here, but their position is fuzzy. It's not as nicely aligned among the different genes. But that's a pattern you observe in vivo. Okay? And again, it was known prior to this paper. That's just their reference. Now the experiment is what happens when you assemble in vitro. And that's what you observe in vitro. So if I ask you, is it the same? Is it similar? Right? Okay, so there were two papers doing this experiment published in that year. One said yes, and the one said no. Okay? These guys said no. The other guys said yes. They had essentially the same data, but the way they show it is different, and the way that they show it makes it look a little more like this, right? So the take-home message from this is, depending how you display your data, you may be tempted to conclude one thing or another. Okay, and that's definitely true in genomics. Okay, because the data is just numbers, and you can represent your numbers in different ways, and sometimes it gives you different answers. So it's probably a good idea to analyze your data multiple ways and be very critical of what you observe, and only conclude when different analyses converge towards the same sort of conclusion. Anyway, that was just a parenthesis. But now other people that do it, and the field has evolved, and especially these guys, I think, won over the other guys. The generally accepted view right now is that yes, DNA contributes, but it's not the only factor. Okay, it contributes because you can see that even just with DNA alone, there are some features that you can see already. You can see this nucleosome-free region. It's not as sharp and neat as here, but you can clearly see that in the promoter region there are fewer nucleosomes. Nucleosome occupancy is lower. You can also see that the very well-positioned nucleosomes they're fuzzier, but they're still there at the right place. Like you have this very nice stripe of nucleosomes. You can sort of see it here, right? And you can sort of see maybe the plus one and the plus two. You know, it sort of looks as a fuzzier version of this. So clearly, the DNA sequence has something to do with where the nucleosomes will go, but it's definitely not the full answer. And now, what these guys did that was very cool